Thanks for listening in. Ciao. And thank you to Sebastian for inviting me to speak. And I'd also like to thank Sebastian and David, Fabio, and Augusto for their recent publication on Archtop acoustics, and I look forward to your future works. Sebastian introduced me, so I will skip that part, and I will jump right into the talk. So the original design of the Archtop guitar is credited to the Gibson Mandolin Guitar Manufacturing Company, and the modern standard Archtop was introduced in 1923 by Gibson as the L5 and designed by acoustics engineer Lloyd Lohr. His design features an arched top and back, elevated bridge, F-hold, and originally had a 16-inch lower bout width and a parallel bracing pattern of the top. By 1935, the L5 grew into a 17-inch lower bout width with an X bracing pattern. The 16-inch parallel brace guitar and the 17-inch X braced guitar set the standard for the Archtop, with many companies and individual makers creating their own designs to compete with Gibson. Throughout the 20th century, the Archtop guitar became a staple rhythm instrument of jazz orchestras, and the go-to guitar for singer-songwriters, most notable Maybelle Carter, who famously played an L5 at the dawn of country music. The Archtop guitar is a historically significant instrument, both for its design and the musical genres and music history it has helped to establish. However, the acoustical behavior of the Archtop guitar has not been studied to the extent of violin family instruments or other guitar family instruments. But the lack of scientific understanding is changing with the recent publication of Archtop Guitar Dynamics by the Violin Society of America papers in 2021 and Sebastian's work and company modal analysis of the free Archtop guitar top plates, published later in 2021 by the Journal of the Acoustical Society of America. And here on this slide, we see a picture of acoustics engineer Lloyd Lohr and the L5 guitar that he designed. And so my work on Archtop guitars really came from guitar making and questions that I had as a guitar maker as to how the instrument vibrates and what could be a few ways of building guitars that would be beneficial with an understanding of the vibrational behavior. Most notably, for the main signature resonances of the guitar body, what are those frequencies and how might frequencies of scale notes that are played on the guitar be avoided in the construction of the guitar body. And so this study was a long process over many years, and slowly the acoustics of the Archtop began to take shape. However, there's still a long way to go and a lot more to study. This is an image of the Archtop top plate CAD model used for the finite element analysis. The FEA was performed with COMSOL Multiphysics and Autodesk Fusion 360. And I will mention that the basis of the study was to create a computer model of an Archtop guitar, and with computer modeling, understand the vibrational behavior, and along with the computer model, construct a guitar to measure the physical qualities experimentally. And so the drawings used for the CAD drawings and the modeling were then cut out on CNC for parts of the guitar, mostly the top, but is also used to cut out the F-hole. And so, as I mentioned, there's the 16-inch and the 17-inch Archtop, and this study focuses on the X-Brace 17-inch guitar. The finite element analysis was guided by Colin Goff's paper, Violin Plate Modes. Colin is an emeritus professor of physics at the University of Birmingham in England. The inputted material properties were consistent with the average properties for Alaskan spruce. Book-matched grain lines were added to the model, spaced 2.5 and 5 millimeters apart. and the grain lines represent the anisotropic nature of spruce with varying Young's modulus values. It is important to note the computer models do not compensate for the fact that an archtop plate is carved and not bent or pressed. The effect on results are higher model frequency values. However, the fundamental eigenmodes, like the one studied here, or the signature modes, are primarily determined by the profile of the arch and the boundary condition of the guitar shape, along with the average material properties. The finite element analysis reveals the modal shapes. The explicit frequencies were determined experimentally. Here's a comparison of the X-braced guitar top. We have the CAD model on the left, and then the actual guitar top on the right. And this is based on Bob Benedetto's design of the L5C Archtop guitar. We have the finite element analysis results. The first set of finite element analysis results are presented. The left-hand column shows an image of the model used for each set of results. The first model is an isotropic square plate. The physics of such a plate are well understood. And the second model is an isotropic rectangular plate with an aspect ratio of 1.25 to 1. This is the aspect ratio of the archtop guitar plate, compared with a 2 to 1 ratio for the violin, meaning the violin plate is 2 times longer than it is wide. Next shows the anisotropic rectangular plate with grain lines. The following model is an anisotropic flat plate shape profile, and finally the arched plate. All of the models have a uniform thickness of 0.187 inches, or I believe 4.75 millimeters. The results of the first model, whose aspect ratio is 1 to 1, show a characteristic twisting mode, primarily influenced by the shear modulus, followed by X and ring shape modes, dominantly influenced by Young's modulus. It is understood that the X and ring mode shapes manifest as the superposition of the fundamental bending mode resonant frequencies, side to side and top to bottom of the square plate. Because the plate is square-shaped, these standing waves are the same frequency, and depending on the phase relation, vibrate in the characteristic X and ring mode. It should be noted that the X and ring modes show up in the violin plate and are referred to as the second and fifth eigenmode shapes. The anisotropic nature of quarter-sawn spruce, with grain lines running the length of the plate, has greater long grain stiffness than cross-grain stiffness, and this disparity, coupled with the aspect ratio of 2 to 1, again meaning the plate is twice as long as it is wide, create the right conditions for the X and ring modes to manifest in an anisotropic plate. As the models progress to become anisotropic and more guitar-shaped, the X and ring modes do not show. There is an X-like mode in the guitar-shaped results, however, it appears to be dominantly governed by the long grain bending mode and arch shape. And these are the results from COMSOL multiphysics software. And this slide shows the 3 working steps of the free plate. First, the standard graduation. Next, F-hole perforations, followed by bracing. The top set of models are anisotropic, and the finite element analysis was performed again in COMSOL multiphysics. The bottom set are the same models, but are isotropic, and the finite element analysis was performed in Autodesk Fusion 360. Again, it is important to note that the fundamental eigenmodes and corresponding eigenfrequencies are dominantly governed by the boundary condition of the guitar shape, the arching profile, and the average material properties. The Fusion 360 models show an X-like second mode and a ring-like fifth mode. However, these are not the same X and ring modes of the violin plate, given the different aspect ratios. The addition of the X brace disrupts the ring shape of the fifth mode, according to the Fusion 360 results. And it should be noted that when the COMSOL models were run as an isotropic guitar plate, there was no ring-shaped mode in the results. And here we have the pinned edge results. This combines the models of the previous two slides with the modification of a pinned edge. The bottom row represents the braced guitar top glued to its sides. There is a visible effect on the amplitude of the vibrating quadrants after the F-holes are introduced, beyond the third mode, revealing one effect of the Archtop sound holes. The first three modes are consistent with the fundamental eigenmodes of the steel string flat top acoustic guitar. The physics of the flat top steel string guitar can be referenced in Trevor Gore and Gerard Gillette's contemporary acoustic guitar design, published in 2011. First mode in that literature is referred to as the T11 monopole of the top plate. The second shape is a transversal flexural pattern referred to as the T21 cross dipole, followed by the longitudinal pattern of the T12 long dipole. So I'm referencing the three modeling results on the bottom row and the first three results there. And now we switch gears into the experimental analysis. Here we see a diagram of the experimental setup for the frequency sweep measurement technique used for the FFT analysis. This technique was utilized in the acoustics lab at Indiana University South Bend, and a sinusoidal frequency sweep of 1 Hz to 3.125 kHz is emitted from a signal generator. The signal transmits through an amplifier and is outputted to the emitting transducer. The transducer is attached to a stylus that contacts the sample at a desired location. As the frequency sweep excites the sample at certain frequencies, a receiving transducer picks up the vibrations and sends corresponding voltages to a preamp, then into an oscilloscope. The oscilloscope is triggered by the signal generator, and the sample rate of the oscilloscope is set to 6.25 kHz, resulting in a 3.125 kHz Nyquist frequency, which is the maximum frequency of the sinusoidal sweep. The sample rate is significant in capturing and analyzing the results without error due to aliasing. The signal is captured by the oscilloscope and inputted into MATLAB for analysis. Received signals of higher voltage corresponding to frequencies of the sinusoidal sweep translate to peaks on the FFT plot, which we'll see next. These peaks are the resonant frequencies of the sample. For free plate measurements, sample rate of 2.5 kHz was used, resulting in a 1.25 kHz Nyquist frequency. Here's the FFT plot for the first free plate sweep measurement. The first 5 fundamental modes or signature modes are all below 200 Hz, and the measured frequencies for the first 5 modes of the standard graduation top plate are 53, 89, 121, 145, and 173 Hz, respectively. So these are the frequencies for the modes of vibration shown in the previous slide for the 3 working steps of the free plate. And here we see an animation of the renderings from the fusion finite element analysis for the standard graduation free plate. The fundamental 5 eigenmodes are in general agreement with Collin-Gauss violin plate mode finite element analysis results. And again, the main difference being the aspect ratio of the respective plates. The black outline is the 0 position of the models. So this is an animation of the finite element analysis results table that we saw a couple of slides ago. And that's the ring mode, the 5th mode in the series. Chladni figure analysis is a technique dating back to the 18th century. In modern times, a sample is inundated with a single frequency correlating to a peak on an FFT plot or spectral analysis. Ground parsley in this case was sprinkled evenly across the plate. As the excited plate vibrates, the parsley settles along the nodes, and the eigenmode for a given eigenfrequency is revealed visually. This clip shows the first 5 eigenmode shapes of the Archtop free plate with standard graduation. The Chladni figures reveal the fundamental eigenmodes are more consistent with Fusion 360 finite element analysis results. Yeah. would be the first mode of the free plate, the twisting mode. This is our X-shaped mode, mode number 2. Third mode. And I only have videos for this first set of Chladni figure results, so don't worry, we don't have to stare at these for the whole talk. They are interesting. I would have played the audio during this, but it would be very annoying for you all. You'd have to turn off your sound. So this is the fourth mode shape. And last but not least, the ring mode. Here we have an FFT plot for the free plate with F-hole perforations. The first 5 fundamental eigenfrequencies all shift lower after the F-holes are cut. Here we have a side-by-side comparison of the finite element analysis results from Autodesk Fusion 360 and the Chladni patterns. For the final working step of the archtop free plate, the X bracing is attached. And here we see the FFT plot for the free plate with bracing. The 5 fundamental eigenfrequencies were measured at 61, 92, 134, 150, and 178 Hertz. With bracing, the fundamental eigenfrequencies shift higher. Here we have a rendered video of the braced finite element analysis results. It should be noted that Chladni figure analysis was not performed for the braced free plate. The bracing interferes with the parsley and obstructs the Chladni patterns, and the modeling shows the first 2 modes switch places. You see the twisting and the long grain mode changing places in this video. And I did attempt to perform Chladni figure analysis, and I could see the tails of the Chladni analysis on the braced plate, and for the experimental while the experimental results showed that the first 2 eigenmodes did not change place, so it is possible. That was just the case for this one top. And here we shift gears again to the guitar body or the corpus. With the braced top plate attached to the sides and back, we see the lowest fundamental eigenmode is a breathing mode, or the air resonance of the newly created cavity. Including this mode, the 5 fundamental eigenfrequencies of the archtop guitar corpus or body are measured at 137 Hertz, and that's the air resonance. 221 Hertz is the main top monopole, or the T11 monopole. 250 Hertz is the T2 or the T21 cross dipole. 281 Hertz is the T11 monopole of the back. And at 315 Hertz is the T12 long dipole shape. We'll see those in the Chladni analysis. And here we have the archtop guitar body in the white. So now the neck has been attached and the hardware has been attached. And the same 5 peaks corresponding to the fundamental eigenfrequencies are measured at 134, 221, 242, 263, and 297 hertz. The first 5 eigenfrequencies of the completed guitar shift lower with the added component coupling of the neck, hardware, and understring tension. And for this measurement, the guitar top is under 169 newtons of downward force due to the string tension. And finally, we have the guitar with finish, a thin layer of nitrocellulose finish under string tension. The fundamental frequencies all shift higher, perhaps due to the slight additional stiffness of the added lacquer, and the final frequencies are 138, 223, 248, 268, and 304 hertz. And it is worth mentioning that these explicit frequencies are for this individual guitar. There are many variables that contribute to the final acoustic signature of an instrument. The effects of arch height, along with recurve thickness and geometry, and the material properties of woods cannot be overstated, and the effects on the final frequencies. And this, of course, shifts throughout the instrument's life. The elastic properties are heavily influenced by how well quartered the timber is milled. McIntyre and Woodhouse's publication titled On Measuring Wood Properties, Volumes 1 through 3, is a very enlightening study on wood's intrinsic properties. In terms of the material properties of the carved plate, violin maker Martin Schlesky discusses in his work The Speed of Sound and Damping of Spruce in Relation to the Direction of Grains and Rays, published by the Catgut Acoustical Society. The cutting the longitudinal grain or radial rays, as is done when carving a top plate, affects the long grain and cross grain Young's modulus, and this results in reduced stiffness and lower corresponding eigenfrequencies, which may account for some of the difference between the predicted frequencies of the finite element analysis and the experimental results. Taller arch profiles result in steeper cuts to the grain and rays, further reducing stiffness. With this understanding, Schlesky writes the effects of the recurve is to decouple the plate as its own vibrating island of effective mass. And this may be especially true for the archtop, considering it does not have a sound post to couple the top and back plates together. And I think this would be a very interesting avenue for further research. That is the effects of arch height on plate stiffness and material properties. And now we'll take a look at the finite element analysis for the guitar body. And this is the lowest resonance of the archtop guitar corpus, and this is the breathing air resonance. The lowest fundamental eigenmode falls in line with both guitar and violin family research. The top and back plates vibrate opposite each other, causing a breathing-like action of the guitar corpus. And here are the animations of this phenomenon rendered in Fusion 360. First, we'll see the top, and the back. So these modes of vibration would be happening simultaneously to create this breathing mode. And here we have another fusion animation of the top plate with bracing and the pinned edge boundary condition. And again, the pinned edge simulates the top glued to its sides. First, we have the main monopole of the top, the cross dipole where the two halves are vibrating out of phase, and the long dipole. Here we have the COMSOL multiphysics results with the same boundary conditions. And we see that they are in agreement. And here we have a side-by-side comparison of the finite element analysis of fusion with the guitar corpus and then the guitar in the white. And we see that the models match the experimental results. And this now getting into future works and how my research has changed since doing this initial set of experiments. And this is a violin measurement rig developed by Joseph Curtin and utilized by the Oberlin Acoustics Workshop. And the rig for violin served as the inspiration for this adapted guitar version. The ability to collect admittance and 360-degree near-field radiation measurements using an impulse hammer offers a clear picture of how the archtop guitar projects sound in space. The frequency set sweep technique utilized for this study is adequate to distill the eigenfrequencies and corresponding eigenmodes of the archtop guitar. However, the next chapter in archtop guitar dynamics will be conducted using these established instrument acoustics techniques. We'll offer a clearer picture of how the archtop behaves in the real world. And it's worth noting that the guitar in this picture is a 1924 Lloyd Loar L5 archtop. And here's a comparison of the frequency sweep technique for the completed guitar with finish. And this is the same plot that we saw earlier. Circled are the peaks of the 5 signature modes. Here we see the acoustic radiation. Again, circled are those same 5 peaks, but this is a representation of how the guitar sounds when you're about a plate length away near the bridge, standing in front of the instrument. And this is also a logarithmic scale on the x-axis, so the plot does look a little different. We see that the signature modes, especially the air resonance, the main top, and the cross dipole, contribute to the projected sound at this location. And we see beyond this initial set of peaks, further peaks, which are also pretty high in magnitude, contributing it to the sound of the guitar in space as well. And so another avenue for research for me is to take a look at this next set of resonant frequencies. And this is another project that I was working on. This is a fun one. This is a 1936 Gibson L4. And I took this to a business that does industrial testing. And they were able to laser scan the outside of this instrument. Here we see the rendered scan from the laser scan of that L4. And this is, I can't zoom in on this picture, but if you look at the rendered model closely, you can actually see the Gibson inlays, all of the scratches and dents in the guitar body, and even the fingerboard. And you can kind of see it in this picture on the first 3 frets, where the wood was removed because the guitar was played so much. And this is a great sounding guitar, and I think part of that is because it has been played over the decades. And so we can take that laser scanned model of the instrument, we can pull it into a CAD software. This is Rhino here. And we can start to do some interesting things. We can remove the top. We can smooth out the arch profile. And this is when we start to ask philosophical questions about the intent of the maker. What was the original profile of the arch top? The profile that we see now has been warped. It's been under string tension for a long time. Some of that was not the initial intention of the maker. And so for these renderings here, we chose a side that we liked better, basically, and we mirrored that side, and we smoothed it out a little bit, and we ended up with a model based on the L4 scan. And here we see that L4 on the right, and then a carved plate matching the arch profile and the F-holes and the thickness of that guitar. So that's sort of where the research is going next. In addition to taking a look at historically significant arch tops and understanding the acoustics of the original designs. And what I find very interesting about this work is that here we are in 2022. The arch top this version of the Archtop guitar is about 100 years old. And we're using all these modern techniques to recreate something that was developed 100 years ago, and in my opinion, in many ways was perfected at that point. And ultimately, this is just fun. There's really, we have the technology, why not use it and do interesting projects like this? And so that's the end of my talk. Thank you all. Thanks to Fan Tao and the VSA and the Oberlin Acoustics Workshop for supporting this work, IUSB, and the National Science Foundation. Are there any questions?
Thanks a lot, Tom. That was beautiful. I do have a lot of questions, but probably also people in the audience. Who wants to go first? Whoever wants to ask, just unmute yourself and ask.
I want to ask some question for Tom. Thank you for the presentation. Thank you, Sebastian, for the invitation. Tom, have you found any trend between free modes and the body modes of the guitar?
I would say that's a very good question and a tough question. The free plate modes of vibration, especially the ring mode and the X mode and the first mode, the twisting mode, that tells us a lot about the material properties of the plate and the mechanical properties of the structure. And in that way, I believe there is a relationship between the free plate and then once it's glued to its sides. I wouldn't go as far to say that any of the mode shapes sort of translate. In a way they do, but I think that's a big question for a lot of guitar makers and people interested in this work. So I would say I wouldn't draw any conclusions at this point.
Okay.
Can you please repeat the questions? I didn't understand. What was the question?
The question was, is there a correlation between the free plate modes of vibration and then the modes of vibration of the guitar once the top is glued to its sides? And
okay,
thank you. The body of the guitar.
Maybe a previous question will be, what is the best frequency response of a guitar between making any correlation? And I think that we don't know that in acoustics of the guitar yet. Having what is the best response of a guitar? Well, at least I don't have this information, but thank you, Tom.
Yeah, absolutely. And I think thinking of the best sounding guitar is kind of the fun of all this work, because in many ways there are acoustic properties or the projected tone of a guitar, a lot of words that we use to describe the sound of an instrument that we could agree are more ideal or more pleasing to our ears. But there's no real formula for making a guitar that's the ideal guitar. It's sort of subjective. We all have our preferences for styles and sounds and music genres. So applying a scientific technique to something subjective, I always say it's science enhancing art.
Thank you, Tom.
Thank you.
I have a question. May I?
Of course.
Go for it.
So thank you for your talk, first of all. It was really, really interesting. And my question was about the parametric models of the CAD models of the plates. Are they parametric? Can you modify them in some way using fusion or some other techniques?
Yes, I could. I will say that for the finite element analysis, I learned how to do that sort of analysis for this project. So I've learned a lot since running these initial models. But I believe the technique that you used in your paper would be more ideal than what I used for this initial study.
Okay, thank you.
Alex, you want to go?
Yes, thank you. Thank you, Tom, for the presentation. And for me, up to this, parsley was something to eat, but now I know how to make use of it in the experiment. So thank you for that. But my question is something different. The plates of the Archtop guitar, I guess they have varying thickness. Is that correct?
Yeah, they do for this study.
So how did you cope for that in the finite element model? Is that all modeled with volume elements, or do you use shell elements for the study?
Yes, there's more of a volume element. So there was one set of analysis that was a uniform thickness, just to show how a square isotropic plate sort of translates into the completed guitar shape. That's the arch and the anisotropic properties. But for the working steps and for the completed instrument, the graduation was considered in the models.
Okay, but I guess you get a lot of degrees of freedom into the model when you try to use it all, model it all with volume elements. So do you get, is computational time an issue for you?
Sorry, can you repeat that, the last part?
Is it with the volume elements, is the computational time, is that an issue, or does it compute fast enough?
It was fast enough running the COMSOL multiphysics. I didn't have a problem. I would have to wait. I mean, it did take time, days really, but I was able to do it all on a cloud basically.
Okay, but it did take days to compute these results this
yeah.
much. Okay.
To do them all, yeah. I'd say one set of results maybe took an hour or two at the most, but to do everything, it did take a while.
Okay, that's like you could with like shell elements, you can also implement the varying thickness, but I guess you could reduce it to minutes.
Yeah.
So you might think about that. You can give the thickness as well. So you model it two-dimensionally and give the thickness into the model, and I think you can reduce it like to minutes from the hours.
Thank you. I will consider that for next time, or hopefully I'll be working with the group here for my future finite element analysis endeavors.
Thank you.
I also have a question for Tom. So hi, and thank you for the talk. Wonderful. I have actually not a question, more a curiosity about how you excited the plate. It was nice to see the Chladni pattern, wonderful. And I'm more curious about instead the transducers you used to inject the sine sweep signal to the plates, and how you recorded them. Which kind of transducer did you use? Thanks.
Sure. To drive the plate, I modified a small speaker with a platform and a stylus, and so it was driven. I turned a speaker basically into a physical driver, and it took a little while, especially for the Chladni figures, find sort of a sweet spot on the plate to get a nice visual representation with the Chladni figures. The receiving transducer is actually a transducer that I made myself, and that was inputted into an oscilloscope. And so I would trigger a measurement with the sweep, and I would capture the resulting waveform. and then convert that into the frequency domain for the FFT analysis. But looking back and also considering about moving forward, I would use an accelerometer and an impulse hammer for those sorts of measurements.
Thank
Does
you
that
so much.
answer? Yeah.
So thank you again, Tom. I joined others. Thanking you for the very nice and detailed presentation. Just a very quick question. I had connection problems during the presentation, so probably lost the reason. This part. Why are you using both Fusion 360 and the COMSOL for the finite element analysis? Probably lost this part, and so.
Oh, sure. Originally, I used Fusion 360 for the finite element analysis, and I was not able to represent the anisotropic nature of the plates, which when I originally submitted the paper for review, that was requested that I show that, and so I used COMSOL multiphysics to introduce the anisotropic nature, and I think the results from the COMSOL multiphysics, they were different from the Fusion 360, and ultimately the Fusion 360 models for these signature modes was a more accurate representation. But I know that in the free plate paper, you guys used COMSOL multiphysics, and your results matched my Fusion results, and I know you had anisotropic properties for your study.
Thank you again, and not only for the answer, but for the presentation. Thanks.
Thank you.
It seems like the anisotropy would not be that important. Once you get right longitudinal direction, everything seems to work. Hena has a question. Nice to see you here, by the way.
Yeah. Hey, thanks for the presentation. I actually have like two sort of future questions, or like I was wondering, have you been speaking to like current makers of the Archtop guitars, like what kind of problems they have or questions on the acoustics that you might be able to solve with using the simulations and measurements? And are you planning to make like a complete string synthesis as well, or study also the interaction between the string and the body, which is kind of very special, I think, in the Archtop guitars?
Yeah, thank you for both of those questions. I would love to talk to Archtop makers about their instruments and about using acoustic analysis for their making. I think there's still a lot of resistance towards that, which I hope changes, especially as we publish more work and also introduce how acoustic analysis could be integrated into a workshop, and what sorts of benefits a maker could see from at least a general understanding of the vibrational behavior of the instruments that they make. But I do hope to bring this study and future studies to more Archtop makers. I hope that they will be open to that. And I will say on future research regarding the string interaction with the Archtop, my interest has sort of gone from understanding these initial signature modes to analyzing historic instruments and also taking a look at the bridge behavior and that interaction of strings in the bridge. I think a big takeaway for me doing all of this work is the importance of that interaction, and so I do hope to learn more about that. I have a few ideas to study that. And I'm open to suggestions also.
About the deformation of the Archtop guitars, like you're just kind of fixing it by hand, no? You don't have you're not predicting the forward problem from like you start with a model, put the force there and compute the creep. You just try to figure it out, no?
In terms of like loading the instrument and the changes of the top under string tension.
Yes.
Yeah, that I've only looked at so far experimentally. I have not modeled that at all.
It's super cool. I think we would love to. I mean, here we have the 300 years old Stradivarius, so it would be nice to see the original, like time traveling somehow.
Yeah, oh, absolutely.
Let me see if nobody else has questions. I have one more.
May I? Can I?
Yeah, go for it.
Hey, hello. Thanks again, Tom, for the presentation. Very interesting. Yeah, just wanted to ask you if you already know what are going to be the next step of your research. Thank you.
I think the next step is to perform modal analysis similar to what the violin research community has performed on the Cremonese violins and historically significant instruments. And so I would like to look at basically the original Lloyd Loar design guitars, and then also the transition from the 16-inch parallel braced instrument to the 17-inch X-braced instrument, and sort of map the acoustic changes from that design change, because from what I've seen so far, it's pretty significant, and I think that would be a really interesting study. And the bridge design also changed at that time, and going back to Henna's question about the string interaction, I see that as sort of a very interesting line of questioning for future research.
Okay, thank you.
Somebody else? I have one more. How did you measure the initial material parameters of your wood? I think I hear you said that you just use the like average Alaskan spruce values.
Yeah, I used values basically similar to what Colin Goff used in his paper, and just known values. I didn't measure the material properties for the wood used for this study. I do talk in the paper. I do talk about the dynamics of instrument wood, but I'll leave that up. I'll leave that for another study.
Okay, thanks. Well, I thank you again for the super interesting presentation. And if nobody else has questions, I think we can finish here. I don't know if you want to stay a bit and we can talk about some future possible collaboration between New York and Cremona.
That sounds very interesting.
Cool. Thanks,
Thank you, everybody, for listening.
Oh, yeah. Fun Tao, please. It's an honor to have you here. Anyway, fun.
Yes, Juan Sebastian, it's very nice to meet you. And because you're talking about collaborations, because Joseph Curtin and I run the Oberlin Acoustics Workshop, and some of the research your group is doing is very interesting. So I'm very open to ideas about collaboration, across both the oceans and even guitars to violins.
That would be lovely. I actually saw that your mail from maybe yesterday, about that there may be a Oberlin workshop this year?
Yeah, we have not had a workshop for the last 2 summers, of course, and we're hoping to have one this summer, but we don't know exactly how many people will come, and so we're trying to get an idea to figure out what we will do. But of course, it's we live in very uncertain times.
Yeah, that's true. But I think we could think of going, Fabio, no?
Yeah, I think so.
Great.
If traveling now is possible, so I think it's something we can plan to do.
Either this summer or certainly in the future, because we've had this workshop now for almost 20 years, and so if not this summer, in a future year, definitely.
Mm-hmm.
For sure.
And I'm curious, if you've done any collaborations, with Claudia Fritz, because she's been coming to the Oberlin workshops for a long time now, and then of course now she's doing a lot of acoustics projects in Europe and France, and
no, we have not collaborated up to now with Claudia. Actually, we are aware of what she's doing in some projects. By the way, some of them are, we didn't collaborate directly, but people working with us in other projects collaborate with her in this. I refer as an example to the, how is the name, Sebastian? The not Bilbao project, should be.
That's the current.
And sorry?
That's the current one, the Bilbao project.
Okay, yeah. So we are aware of what she is doing, but up to now we didn't have the chance to collaborate with her. But of course, that's a possibility for also even the short future.
Yeah, because one of the things I noticed is that I think the different groups have different complementary skills and strengths. So I think at least in the area of violin acoustics now, my opinion is that some of the most interesting work in the future actually will consist of much more interdisciplinary, tying these different areas together. So it's not just about, plates, the vibrational behavior plates, but connecting that, different areas, and most of us, we may have a particular skill in one area, but we don't have skills in other areas.
I totally agree with you, Fan. Basically, she is very expert with listening tests and perceptual interpretation of this.
Yep.
We gained some expertise on analysis and modeling, but I believe we have to pursue a way of finding the possibility to merging the two, not only for collaborating with the Claudia, but for making a step ahead in as an example, in knowing what's the perceptual effect of some constructive modification to the instrument.
Yeah. Mm-hmm.
But I totally agree with you. That's a step. It happens quite often that research groups focus on their expertise and excluding the possibility of having some joint projects that they want to pursue their path. And let me say that also the pandemic didn't help in this, because we didn't have the opportunity to meet other researchers apart these kind of meetings like today. But I totally agree with you. That's something we have to pursue.
Yeah,
and learning this from you, this as a suggestion from you, is a very
yeah. Okay, so I'm very encouraged. I mean, I don't think we need to get into details in this meeting. So except to introduce myself, and hopefully we can work something out. And the other things, I don't know which one of you is on my mailing list, but I do invite you. We have future first Fridays of the month. We have online presentations. So I was wondering if you might be interested in giving a presentation on some of your work at at next month's presentation in March or April, or in the future. So but we can be in touch by email about that. My question would be, who's the main person that I should correspond with in your group?
I'm across the different laboratories, but Sebastian probably is more focused with respect to the musical acoustics laboratory,
okay.
While I work on a different laboratory. So if you get in contact with Sebastian, but basically he will inform me about what's happening, for sure.
Okay, thank you very much.
Thank you, fans, for this encouragement.
Okay, thanks again to all the people present, and see you in the next meeting, maybe next or in the following month. Thanks again, Tom. It was really nice to meet you.
Thank you, Sebastian.
Thanks.
Likewise.
Thanks, Tom, for the presentation, and thanks, Sebastian, for the organization. Bye.
Bye.
Bye.